Alright, calculus students, today we are going to take a look at a lesson about limits. This is something we'll hit a little bit more during the year as well, but I want you to have a pretty firm grasp of this before the year starts. I'm going to start off by showing you graphically what we're talking about, and then we're going to look at some that we do algebraically, and then a few of them that we'll do using a table. Actually probably just one of them. So let's just kind of take a look at what we're talking about when we talk about limits on a graph. So this is some piecewise function, we'll just call it f of x, and I've got a couple points here, a couple holes, a couple jumps. This is a vertical asymptote right here, okay, and here we have a horizontal asymptote at, I didn't really draw it in there, but we'll say it's at y equals 1. Okay, so here we go. We'll start with a real basic one, this point right here. As x, as my x value gets closer and closer and closer to the number 1, then my y value is getting closer and closer and closer to the number 2 until eventually we end up at the point 1, 2. Alright, and it doesn't matter which direction I move from. So let's say I'm at maybe x equals 0.9, maybe my y value is like 1.9. At x equals 1.1, maybe my y value is 2.08 or something like that. As I move closer and closer and closer to 1 from either direction, as I move here closer and closer, x equals 1, or here, x equals 1. So really what we're doing is we're kind of thinking that we're moving along the number line, but it has to follow this path here. All right, as x gets closer and closer to 1, my y value, using this number line, is getting closer and closer and closer to 2, and eventually we do get to that number 1, 2. So that's pretty basic. Now this one looks a little confusing possibly. Out here at x equals 2 and y equals 3, we have a hole in our graph, right? But the limit concept still works the same. Even if there's a hole in the graph, it's not a big deal, because really we're talking about what we're getting close to. So as x equals maybe 1.9, my y value is probably like 2.9 or 2.95 or something like that. On the other side, as x equals 2.1, we probably have the same thing going on. It's a little bit below 3, so 2.9, 2.95, something like that. If we actually knew what this graph was, we could calculate it a little bit easier. All right, those close values, but it doesn't really matter. All we know is that as we're getting closer and closer and closer to x equals 2 from either side, my y value is getting close to 3. Now, when I actually get to the point 2, 3, there's a hole in my graph. So I don't have a point there at 2, 3, but my limit, right, what I'm getting close to is 3. Over here we have a little bit of an interesting thing going on. Okay, as I'm coming toward, this would be x equals 4, as I'm coming toward x equals 4 from the left side, my y value is approaching 1, and when I actually get to 4, my y value is 1. On the right side, as I'm getting closer and closer and closer to 4, my y value is getting closer and closer to negative 2. It never quite gets there, all right? It does get there here, right? It does not get there here. You cannot have both of these filled in, otherwise it would not be a function. It would not pass the vertical line test. You could have holes in both of them, that's fine. Something doesn't have to have a value at every vertical line, like right here it doesn't, okay? So one of these can be filled in, one not. Now in this case, the limit as x equals 4 is a different answer depending on whether I'm coming from the left side, in which case it's 1, or whether I'm coming from the right side, in which case it is negative 2. So if they do not specify a direction, we cannot answer this question. We would say the limit does not exist. If they do specify a direction, then we can either say it's up here at 1 or it's down here at negative 2. And let's look at a couple other examples. What about x equals 0? As I get closer and closer and closer to x equals 0 coming from this right side, my graph is going down. Remember earlier I said this is supposed to be a vertical asymptote here. So in that case, I don't really have a number that my y value is approaching. It just keeps going down, 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 down. It gets increasingly large in a negative direction. Okay? It doesn't have a boundary. There's a couple things we can say there. We can say that the limit does not exist, or we can actually say that the limit is negative infinity. Technically, your limit has to equal a number. Infinity is not really a number, it's more of a concept, right? But we are allowed to answer infinity or negative infinity as our answer, right? You can, probably the best way to say it is the limit does not exist because the y value is approaching negative infinity. Right now over on the left side though, as x approaches 0, we do have a point here. Alright, we have a point at 4. Okay, as I'm getting closer and closer to 0 from the left side, so -1, -0.5, -0.2, -0.1, -0.01, and so on, my y values keep getting closer and closer and closer to the y value 4. Alright, but over here on the right side, as I come, 0.5, 0.2, 0.1, 0.01, my y values are 0.5, it looks like it's maybe 0. At 0.2, maybe it's down here at about -2 or -3. Right, at 0.1, it's probably way down here at like -10 or even farther. -0.01, we're starting to look at possibly -100, even farther than that. And as I get closer and closer to 0, my y value just keeps getting bigger and bigger and bigger in a negative direction. It's increasing in a negative direction. If you're thinking on a number line, it's obviously a smaller number technically, but a lot of times we'll say things like increasing in a negative direction or something like that. All right, and lastly, we've got this out here. As x approaches negative infinity, in other words, as x gets increasingly large in a negative direction, what is my y value? Now remember at the beginning I told you we're gonna say that there's a horizontal asymptote here at 1. So we would say that 1, all right, the y value of 1 is our limit. In this case, it will never reach 1. It'll never touch that vertical or that horizontal asymptote, but it is our limit. We're getting really, really, really close to it. If I put in, x equals -50, our y value would probably be like 1.01 or even possibly closer to 1 than that. Right? So that's kind of the idea of a graphical look at limits. So let's look at how the notation looks, and I'm going to do a bunch of limits on this graph with some notation just so you get a feel for that, and then we're going to go ahead and look at some algebraically. So the limit as x approaches 1 of my function. So as x gets closer and closer and closer to 1 from either direction, all right, my y value is getting close to 2, so that's pretty easy. That answers 2. Well, what about as x approaches 2? As x approaches 2, from either direction, my y value is getting closer and closer to 3. I don't actually have a point there at 2, 3, but my limit is still 3. Right, so it's a pretty easy one. What about the limit as x approaches 4? Okay, well, as x approaches 4 from the left, talked about this earlier, I'm getting close to 1. It approaches 4 from the right. Now when I say from the right, I'm actually moving kind of toward the left, but we say from the right and from the left. All right, I get 1 here and I get -2 here. They're different answers, so in this case we would say the limit does not exist, and you can put DNE for does not exist. If you want to write out does not exist, that's fine. All right, what about this one? The limit as x approaches infinity. All right, I kind of messed up on my infinity sign. That's a better one over there, but that's negative infinity, but infinity. Okay, well, as x approaches infinity, as x gets extremely large in a positive direction, my y value is also getting extremely large in a positive direction. All right, so this answer would be infinity. Man, that's horrible. Sorry about that. All right, as x approaches negative infinity, we just talked about this one right at the end. As x gets extremely large in a negative direction, my y value is settling down toward this asymptote of 1. Okay, so this answer would be 1. All right, what about the limit as x approaches 0? As x approaches 0 from the left, my y value is at 4. As x approaches 0 from the right, my y value is, well, it's decreasing without bound. All right, getting extremely large in a negative direction, negative infinity, however you want to phrase that. Since those answers are different, this would have to be a does not exist again. Now, if we do want to specify a direction, this is how we do it. All right, you can see there's a plus sign here and a minus sign here. Now, what the minus sign means is from the left. Now, when we're approaching 0 from the left, that's kind of easy. It's negative numbers. When we're approaching 0 from the right, it's positive numbers. But over here, I have 4 from the right. All right, that's, yes, it's positive numbers in this case. But if I went 4 from the left, it would still be positive numbers like 3.8 and 3.9. So the positive and negative sign there doesn't necessarily mean positive and negative numbers. It means the direction you are coming from. Negative meaning coming from the left, and positive meaning coming from the right. So what is the limit as x approaches 0 from the left? All right, so here's x equals 0. As I approach x equals 0 from the left, my y value is getting very, very, very close to 4. So this answer would be 4. What about as x approaches 0 from the right? Okay, as x approaches 0 from the right, my y values are getting very, very, very large in a negative direction. They're decreasing without bound. We can say does not exist, but a lot of times we'll actually give an answer of negative infinity. All right, the limit as x approaches 4 from the right. as I'm coming from the right toward x equals 4. I end up at this hole here. The hole itself doesn't matter. All right, my y value is getting really, really, really close to -2. Okay, so those are how you do some of those limits on a graph, right? And anytime we do some of these next limits, which we're going to do algebraically, you could always graph them and look at them, but you do need to know how to do them without a calculator for the most part. All right, so let's take a look at some that do not have a graph, it's just algebra. The first thing you always want to do is just plug the number in and see if it works. All right, so the limit as x approaches 1 of this. So I plug in 1, I get 1 squared plus 2 times 1 minus 3. 1 plus 2 minus 3, 3 minus 3 equals 0. There you go, that's our answer. If I were to actually graph this, the point 1, 0 would be on this parabola. All right, as I approach 1 from either direction, all right, I would be getting values really close to 0. When I actually get to x equals 1, I would have a value of 0. Most of the time, though, it's not going to be that easy. So let's look at what happens when we try to plug 4 in here. Then we try to take our x equals 4 and put it in here, substitute it in, see what happens. We get 4 squared minus 16 over 4 minus 4. 16 minus 16, 4 minus 4, we get 0 divided by 0. And that's a very, very, very common thing in calculus, 0 divided by 0. 0 divided by anything is 0. But anything divided by 0 is undefined. It's basically either infinity or negative infinity. So the question is, well, what in the world does 0 divided by 0 equal? Well, if we follow the rule of 0 divided by anything equals 0, we have to say that it's 0. But if we try to divide by 0, it's undefined. It's basically getting extremely large or extremely large in a negative direction. So which rule do we follow? Well, it just so happens it's kind of an in-between. And basically the answer is it's in between 0 and infinity. Yeah, really narrows it down a lot, right? So basically 0 over 0 can equal anything. So what you have to do is do some math, usually factoring. Sometimes there's a little bit of other stuff, but factoring is usually pretty helpful. So let's factor x squared minus 16. You guys should remember how to do that from like Algebra 1 class. X plus 4x minus 4 over x minus 4. Keep my limit out front until I actually substitute the 4 into the problem. Now you'll notice very nicely right here what's going to happen. Now this x minus 4 and this x minus 4 are going to cancel each other out. That right there, if you think about putting 4 in here, 4 minus 4 is 0, 4 minus 4 is 0, that's the 0 over 0 problem. Now I substitute 4 into what remains. 4 plus 4 equals 8. If we actually looked at this on a graph, all right, this right here would look exactly like this line. All right, simple line, x plus 4, except that at the point 4 comma 8, there'd be a hole. Okay, and you've seen those before, x plus 4. Okay, so 1, 2, 3, 4. All right, slope of 1, something like that. Okay, that's basically what we're looking at. And right here at 4, 8, we would have a hole in our graph. So as x approaches 4 from the left or from the right, the y value is getting really, really, really close to 8. When it actually gets there on the original, we get 0 over 0, so it's undefined. All right. In this case, remember I said 0 over 0 can equal anything. In this case, it equals 8. All right. Or it's getting close to 8 if you want to talk about it in that way. But 0 over 0, very common thing in calculus. Let's take a look at another one where we get that. So x approaches 3. 3 minus 3 is 0. 3 cubed is 27. 27 minus 27 is 0. So we get this 0 over 0 thing again. So let's factor. All right, x cubed minus 27. Hopefully you remember how to factor sum of cubes and difference of cubes. So the limit as x approaches 3 of x minus 3. All right, if you forgot how to do this, all right, this is x cubed minus 3 cubed. We take the x, the 3, the x squared, 3x, and the 3 squared, which is 9. The signs, it's same, opposite, always positive. So this is a negative sign, so this is the same. This is opposite, this is always positive. All right, now, you'll notice right here again, these are going to cancel out. That, if I tried to put the 3 in here, 3 minus 3 is 0, 3 minus 3 is 0. That's the 0 over 0 problem. Now I can take the 3 and put it in here. 3 squared is 9. 3 times 3 is 9, plus another 9. I don't have anything in my numerator, so there's a 1 there. Get my limit back in. Actually, no, I don't need my limit. I already put my 3 in. So 1 over 9 plus 9 plus 9, 1/27th. Alright, take a look at another one. This one, we won't be able to factor it really. Okay, something like that. Alright, so in this case, we're going to use conjugates. You guys remember conjugates hopefully from either Algebra 2 or pre-calculus. So we're going to multiply by the square root of x plus 3 plus 2 on both the top and the bottom. Now most of the time when you've done conjugates, you've talked about doing the conjugate of the denominator. There are times where we may need to do the conjugate of the numerator though. So it's okay to do the conjugate of the numerator if you absolutely have to. You just need to do whatever helps you figure out the problem. Okay, so square root of x plus 3 times square root of x plus 3 is x plus 3. Square root of x plus 3 times 2 is a positive 2 root x plus 3. When we take negative 2 times that, we get negative 2 square root of x plus 3. They cancel each other out. Remember, that's the idea of a conjugate, is that when we multiply, if you're thinking FOIL, probably heard that first, outer, inner, last, the O and the I terms are going to cancel each other out. Negative 2 times positive 2 is negative 4. Now up here, we are not going to multiply this out. Okay, you'll see why in just a second. So x minus 1, the square root of x plus 3 plus 2. Alright, I still have my limit out front because I have not substituted the 1 into the problem yet. I'll do a tiny bit of simplifying here. Still not going to multiply the numerator out. X minus 1, square root of x plus 3 plus 2 over x minus 1. And once again, we see we have some canceling. That, think about the 1 here. 1 minus 1 is 0, 1 minus 1 is 0. That's the 0 over 0. We didn't really even try it up here. Should have. We always should start by trying it. 1 minus 1 is 0. 1 plus 3 is 4. Square root of 4 is 2. 2 minus 2 is 0. So that was 0 over 0. Now we substitute the 1 in. So 1 plus 3 under the root plus my 2. Square root of 4 is 2. 2 plus 2 is 4. Alright. What about this one? X approaches 2. Alright, I've got x cubed plus 5x squared minus 18x plus 8. Man, that is ugly. Factoring that, I don't really want to factor it. I could try, but I'm going to use division. Now, it's technically x minus 2 divided by x cubed plus 5x squared minus 18x plus 8, but I'm going to do the division the other way for just a second. I'm going to do x cubed plus 5x squared minus 18x plus 8 divided by x minus 2. Get a couple parentheses here so I know exactly where my division is. And we're going to do that using synthetic division. It makes things a lot easier. 1, 5, negative 18, 8, x minus 2. So I put a positive 2 out here. We always put the opposite. Okay, bring the 1 down. 1 times 2 is 2. And then we add 5 plus 2 is 7. 7 times 2 is 14. We add, we get negative 4. 2 times negative 4 is negative 8. We add, we get 0. This is my remainder, so there's nothing left. X squared plus 7x minus 4. And we always drop down from x cubed down to x squared. And I'm going to keep that x minus 2 out front. So what we've done is we've said, okay, since this can be divided by x minus 2 without a remainder, that means it can be factored to this right here. So I'm going to bring this back over here. I'm going to write my limit as x approaches 2 of x minus 2 over x minus 2 x squared plus 7x minus 4. Now once again, I didn't even try putting 2 in at the beginning. I probably should have. Part of the reason I keep forgetting to do that is I designed all these so that you'll get lots of 0 over 0 ideas. Alright, but let's check it real quick. 2 minus 2 is obviously 0. 2 cubed is 8. 2 squared is 4 times 5 is 20, so there's 28. 18 times 2 is 36, so 28 minus 36 is negative 8, and negative 8 plus 8 is 0. So it was going to give us a 0 over 0 problem. Once again, we see canceling. There's a 1 that remains in the numerator, so I'm going to substitute the 2 in now. We get 2 squared plus 7 times 2 minus 4. 2 squared is 4, 7, that's times 2, not 7 squared. 7 times 2 is 14. 4 plus 14 is 18. 18 minus 4 is back to 14, so 1/14. All right, what about this one? As x approaches 0, the sine of x over x. Now, it doesn't really matter on this one, but the calculus we do is always done in radians. All right, now sine of 0 radians, sine of 0 degrees, they both give you the same answer, but if you get out into, you know, the sine of pi over 4, we got to be doing that in radians. The sine of 10 does not mean the sine of 10 degrees. In calculus, we're going to do everything in radians. Okay, so sine of 0, well, sine of 0 is 0, and obviously in my denominator I get 0, so this is 0 over 0, but this is a little weird one because we cannot factor it. So in this case, we're going to look at a graph, okay? So I'm going to get my calculator up here, get this thing turned on. I have a bunch of functions already in my y equals. The first one there, you can actually see x minus 1 divided by x plus 3 minus 2. That was the one we did up here earlier. So let me show you real quick what happens on that one. I don't have any of these equal signs highlighted right now, so that way I can just do one at a time. So I come over to the equal sign, I hit enter, puts that box there, I'm going to graph that. Alright, so you can see this graph kind of looks like half a parabola. There's maybe another half down here, but it wouldn't be a function if it was down there. And I don't know how easy it is to see that. Let's see if we can get, there's a tiny little kind of glitch in the graph right there. Let me zoom in a little bit. So we'll just put a box around it. So I'm going to come up here and see if I can, well, I didn't go up, I went the other direction, that didn't help. Alright, I'm going to come up here. You know what, quit that. I'm going to try to just zoom in just at the very center by a factor of 10 and see what happens. I don't know if it's a factor of 10, it's going to go off my graph, isn't it? Alright, change my window. Alright, so let's just, let's add about 5 to each of these. These numbers are actually pretty nice numbers to use. I'll explain more of that in class at some point. But I want to take that, I want to just add 5 to it, kind of move it up a little ways. I'm going to add 5 to this. By just adding 5, it keeps my pixels constant. So, alright, there you go. You can see it. There's just this one little pixel that seems to be missing in your graph right there. That, if I trace this, alright, you can see it's counting out there on the x values by 16ths or something like that. I'm getting really close, and right there when I hit x equals 1, there's nothing there for y. That's that hole right there. And if I come a little farther, the cursor shows up again. Nothing. There it is. So on either side of it, you'll notice there, barely below 4. There I'm barely above 4. Okay, so my limit was 4. Right. So let me get back out of here. And back to that. Alright. But let's do this one right here. Let's take a quick look at this graph. Alright, so go to my y equals. I'm going to go over there to this equal sign. I'm going to get rid of this. I'm going to come down here. There we go. I'm going to graph this. Once again, we'll kind of see what it looks like. Alright, so there's what it looks like. You can't really see the hole, and that's partly because the axes are on, but I'm going to zoom in again. Okay. And I'm also going to turn the axes off real quick, so that's under format. Turn these axes off, graph it. So you'll be able to see right there up at the top there's a missing pixel. Alright, so that's my 0 over 0, that's where that hole is occurring. Now how do I find that? If you remember back when the axes are on, it looks like it was right at 1. There's also another way you can do this. We can go to our table. Okay, so we go to our table here, right here on F5. Okay, and you can see right there at 0 there's an error. But this doesn't give me a whole lot of idea of where it is. So it's 0.84, so that's kind of close. So what I'm going to do is I'm going to go to my table set. I'm going to start at -1, and I'm going to count by 0.1 instead of just by 1s. Alright, and I'm going to go back to my table. So as I get closer and closer and closer and closer to 0 now, you can see those y values are getting closer and closer and closer to the number 1. We're at 0.998. Both sides, looks like we're getting right there toward the 1 value. We'll actually look at this problem a little more in detail throughout the year, actually early on in the year. Alright, so this one, just by looking at the table, we can see that the answer is 1. Alright, keep moving. Got kind of a weird function here. This is sometimes called the floor function. This is basically, it says to round everything up. All right, so sometimes there's one that looks like this, and that one would be to round everything down. All right, so in other words, if I had stuck like a 5 in here, 5 divided by 2 is 2.5, I round it up to 3. If I had something like this, and I stuck a 5 in, 5 divided by 2 is 2.5, I'd round it down to 2. Okay, but we're going to do this one. So I'm going to approach 6 from the left. That means I'm going to use numbers like 4, 5, 6, and so on. Or maybe even 5.7 or whatever. So if I try to put 5 in here, 5 divided by 2 is 2.5, and I'm going to round it up to 3. If I put 5.6 in here, divided by 2, I get 2.8, I round it up to 3. 5.8, I divide it by 2, I get 2.9, I round it up to 3. When I finally get to the 6 divided by 2 is 3. I don't have to do any rounding there, so my answer is 3. Now if I went to 6.2, 6.1, something like that, and divided by 2, I'd be barely over 3, but I'd round that up to 4. So my limit as x approaches 6 from the left, 5.7, 5.8, 5.9, etc., is always 3. If I was doing it from the right, my answer would actually be 4. This is what's called a step function. It kind of looks like this, where your graph comes out, and then it does this, and this, and this. It kind of looks like that. Okay, so when we hit, in this case, because we're dividing by 2, every time we hit an even number, it jumps. All right. But in this case, our answer would be 3. Just kind of thinking through that process. All right, we didn't actually have to graph it. We just kind of thought through it. Didn't really have to do any algebra work. All right, so that's kind of a bunch of numerical type algebra things. Now here's a little bit different. We're going to do limits as x approaches infinity. We did that way back at our original picture. As x approached positive infinity, we went up to positive infinity. As x approached negative infinity, remember our graph had that asymptote out there at y equals 1. To do those algebraically, instead of graphing them and looking at it, what we do, we have a very basic rule, and later on I'm going to teach you some shortcuts on it, but the rule is go ahead and divide everything by the biggest power in the denominator. Not necessarily just the 2, but x squared in this case, or in this case x, or in this case x cubed, or whatever. And these bottom ones here, our biggest power in my denominator is just the x. Here it's x cubed. All right, so I'm going to take everything, x squared over x squared, plus 2x over x squared, 3x squared over x squared, minus 4x over x squared, minus 7 over x squared. Still have my limit out front, x approaches infinity. Now the reason that we do this, if I kind of go back, let me back up a little bit. If I try to plug infinity in here, infinity squared is infinity, 2 times infinity is infinity, infinity plus infinity is infinity, infinity squared times 3 is a really big infinity, 4 infinity, 7, you're basically adding and subtracting, multiplying a bunch of infinities, and it's hard to keep track of which infinity is going to be bigger than which other infinity. They're just really, really, really big numbers. And there are different sizes of infinity. This gets into some set theory concepts, but if you think about it, if I asked you how many, even numbers are there, well, you would hopefully respond there's an infinite amount of even numbers. And then if I said, well, how many multiples of 3 are there? Well, hopefully you would say that there's an infinite amount of multiples of 3. But you should understand that there's more multiples of 2 than there are multiples of 3 within like a certain boundary, say from 0 to 100. All right, so this idea of infinity kind of having different sizes is a kind of weird thing to wrap your mind around. But when you finally get into this and you start plugging infinity in here and infinity in here, they might be different size infinities, and one might actually be bigger than the other. So that's kind of what's happening here as we do this type of math, is we're going to deal with some of that, okay? All right, so x squared over x squared is 1. 2x over x squared is 2 over x. 3x squared over x squared is 3. We get 4 over x, and we get 7 over x squared. Hopefully all that makes sense there. So remember, as long as we do, basically what we did is we multiplied the top by 1 over x squared, and we just did it individually, kind of way back over here. We multiplied the bottom by 1 over x squared, we just did that individually, and we got these, we simplified them, we still have my limit as x approaches infinity out front. Now we can do some math. If I take 2 divided by infinity, 2 divided by a really, 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 really big number, the answer is so close to 0 that we don't need to worry about it. So we say basically it equals 0, so 1 plus 0 over 3 minus 4 divided by infinity, same idea. It's just really, 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 really close to 0, so small that it doesn't really matter in our calculations. And then 7 divided by infinity squared, once again, very, very, very close to 0, so our answer is 1/3. So as x goes off to infinity, as x gets extremely large in a positive direction, my y value is going to settle down. It's going to get really close to 1/3. It's probably going to be some kind of horizontal asymptote. Okay, let's look at it here. What do we got going on? So the limit as x approaches infinity. If I try putting infinity into this, I get infinity over infinity. Okay, which one's bigger? Hopefully you'll understand that infinity squared is bigger than just regular infinity, but we're going to follow that rule, divide everything by the biggest power in the denominator, and the limit as x approaches infinity. So I get 5x plus 7 over x, 1 minus 4 over x. I still have my limit as x approaches infinity. So I get 5 times infinity, which is infinity, plus 0 over 1 minus 0. So the zeros don't really matter. I get infinity divided by 1, which is infinity. So in this case, as x gets extremely large, y also gets extremely large. Right? It's kind of like our first graph, actually. All right, let's take a look at negative infinity here. In this one, got x squared plus 3x minus 4x cubed plus 8. Now this can be factored. It really doesn't help to factor this when we're doing infinity and negative infinity, though, so I'm not going to bother. We're going to divide everything by the biggest power in the denominator, which is x cubed. Now, some of you may start noticing a few kind of shortcuts on these infinity ones. Limit as x approaches negative infinity. We're going to talk about some of those shortcuts in more detail later on throughout the year. All right, here we have 1 over x, 3 over x squared, minus 4 over x cubed, 1 plus 8 over x cubed. My limit as x approaches negative infinity. I'm kind of running out of room here. All right, but I think we can fit it in. So basically 1 divided by negative infinity, it's still so close to 0. So I get 0 plus 0 minus 0 over 1 plus 0. Well, 0 divided by 1 is 0. So my answer here is 0. All right, we're almost done. 2 more examples. One more with infinity again, right, and then 2 kind of different ones. All right, the limit as x approaches negative infinity. Okay, so once again, I'm going to divide everything by the biggest power in the denominator. So I have my limit as x approaches negative infinity of 2x squared over x plus 7x over x minus 8 over x over x plus 1 over x. So limit as x approaches negative infinity of 2x plus 7 minus 8 over x, 1 plus 1 over x. So I get negative infinity plus 7 minus 0, 1 plus 0. Well, negative infinity plus 7 is still just negative infinity. And then negative infinity divided by 1 is also negative infinity, so that's my answer. All right, 2 more. This one's a piecewise function. The limit as x approaches negative 2, and that's a positive sign there, so that means from the right. Okay, now what we're going to do is we can think about this kind of in 2 different ways. This, remember, is everything that says x is less than negative 2, so everything off to the left side. Well, if it says from the right, then I really don't even care about that. I don't even have to look at it. I'm going to look at it briefly just to point something out to you, but I technically don't need this at all. If I take negative 2 and I plug it in here, 4 times negative 2 is negative 8 plus 2 is negative 6. As x approaches negative 2 from the left, the y value is getting really, really, really close to negative 6. But it doesn't have an equal sign here, so this is kind of the open circle part of the piecewise function. Now down here, negative 2 squared is 4, and 4 minus 7 is negative 3. This does have an equal sign. Right, so this is kind of the filled in circle. And as I'm going from the right, so that means numbers like 0 and negative 1 and negative 1.8 and so on, I'm using this function to find my answer. So in this case, my answer would be negative 3. Now, if it did not give a direction here, we would evaluate both limits, the limit from the left and the limit from the right, and if they are different, we would not have an answer. In this case, they were different. We had negative 6 and negative 3. If they are the same, all right, then you can have a limit. If they're not the same and they don't give you a direction, you cannot. Okay, and then finally, last one. Find the slant asymptote of this function. Now this kind of has a limiting idea, all right, but we're not actually going to do a limit on here. A slant asymptote basically says, okay, if I take this divided by this, it's kind of this weird looking graph. Let me show you what it looks like. I have it here on my calculator. So y equals, it's this one right here, but let me get rid of this one, and let's graph this. Let's kind of go to zoom. Previous, I think, is what we want. And I got to turn the axes back on as well. So format axes on. Alright, so this is what our graph looks like. So as you can, hopefully what you can kind of see here is this graph curves like this. There's actually a vertical asymptote right there, x equals -2. But then there's also what we call a slant asymptote that's cutting right through here. And that's what we want to find. It's really this idea of as x approaches infinity, kind of going out this way, technically to the right, point my pin to the right, all right, then the y value has to be approaching something. Well, it is approaching infinity. It's going to get extremely large. As x approaches negative infinity, it's kind of following this curve here, all right. The y value is going down, so it's approaching negative infinity, right? But there is a limiting idea, and that's what we're going to look at here. And the easiest way to do that is just by synthetic division. I'm going to take my 2, and my -7. I'm going to put my opposite, so -2 out in the box. I'm going to bring this 2 down, multiply, get -4, add, get -2, 4, and -3. So what this means is that this is the same as saying 2x minus 2 minus 3 over x plus 2. This right here is all I'm really concerned about. This is just kind of the leftover, the remainder part. Okay, so I want to show you what happens when I graph y equals 2x minus 2. I already have that here. So let me come down here and get this up there and graph both of them at the same time. So you can see I've got my original function there and then this 2x minus 2 and I graph it. Right there you get this whole straight line, and you'll notice that this is getting very, very, very close to that straight line. It looks like they almost touch. They technically don't. Down here you can't see it quite as well. If I were to zoom out, you'd be able to see a lot better. It's going to look a little blurry actually, but there's the curve. Doesn't look very curved, and there's the line, and you can see how they're almost exactly the same here, and you can barely even tell the difference there. If we were to actually go to our table, I'm going to change that so it's starting at, how about 10 and counting by ones. Alright, you can see how close they are together. So that's the curve, that's the line, curve, line, curve, line. They're very, very, very close together. Hopefully you can see those numbers. Alright, and the farther out I go, the closer and closer and closer they get. Alright, the curve versus the line. Alright, so when I'm way out there at x equals 21, alright, the curve is at 39.87. There's probably, my guess would be a few other decimals there. And then the line is exactly at 40. Alright, so, but that's kind of what's going on there. They're getting very, very close together. If we went the other direction, we'd notice the same thing. Now, right here, you'll notice they're not very close together. Okay, but that's not kind of out toward infinity or negative infinity. But the bigger I get, in this case going toward negative infinity, once again you can see how the y values are starting to get very, very, very close to each other. Alright, so that's what's going on there with slant asymptotes. Alright, like I said, you need to have a general idea of limits before we start the year. I know this video might be a little bit long, but you need to watch through it. I do also have a homework sheet that I usually give out during the year to the pre-calculus students. That's why it says Honors Pre-Calculus Limits Worksheet. What I will probably do is either put this up on RenWeb or something like that, and I expect you to be able to do these problems. There's basically, in this case, 11 of them on the front. There's a total of 21 questions altogether, so you've basically got a front and a back page, and I do expect you to be able to do that. We will check that during the year, so you need to have that done. Alright, if you've got questions, you just need to let me know when we're in class at some point, and or come see me outside of class at some point as well. So limits. Welcome to calculus, and hopefully we'll have a very, very, very good year.